Hello, this is lesson 8.5, Solving Special Systems. This will be from pages 259 to 264. So again, we are working from standard EE8. I can solve systems of two linear equations and two variables algebraically using elimination with multiplication. Remember when we were back in lesson 7.4 a couple weeks ago? We discussed that an equation can have one solution, no solutions, or infinitely many solutions. Well, this is also true of systems of equations, and we are going to see how they can have one solution, infinitely many solutions, or no solutions at all. Okay, this is page 259. If you need to pause the video to get to that page, please do so, and then I will see you back in a moment. So page 259, we have an explore activity, and I wanted to show you how this looks with graphing to figure out whether something has one solutions, infinitely many solutions, or no solutions. So I'm going to slide up just a little bit. This is some linear equations that I have graphed, and I've got 3x minus y equals 1. If you wanted to graph that, you'd have to get that into slope-intercept form, and then you could find the y-intercept and then the slope of the line. This one is x plus y equals 7, and this one is x plus y equals 3, and 2x plus 2y equals 6. Now down below that, and hopefully I can get this all on one page, probably almost. This is three different systems of equations. So the first system I have is x plus y equals 7. That's this line. And I have 3x minus y equals 1. That is the green line. You can see right here, 3x. I'll move that down. I'll write that over here. 3x minus y equals 1. That way you can see that. So that's the green line, and that's the pink line. So if you can see from the graph, what happens when you graph these two lines? Exactly, they intersect at this point right here, which happens to be 2, 5, right? So we have how many solutions to this system of equations? Well, we have one point of intersection. So we have exactly one solution. And that solution we decided was at the point 2, 5. Okay. Let's take a look at this system of equations. We have x plus y equals 7 again. That's the same line here, the pink one. And then we have 2x plus 2y equals 6. 2x plus 2y equals 6 is the other pink line. I should have made that a different color. I think I will make that orange. I don't know if I can do that anymore, but let's try it. Probably not going to be noticeable on the camera too much. The orange line, okay? 2x plus 2y equals 6. So this is our other system. We have the pink line and the orange line. What do you notice? Is there a point of intersection between these two lines? The whole thing. This line, that line. No, right? Those two lines will never ever meet. They are parallel. Parallel means that if they can go on forever and ever, they are the same distance apart forever and ever into space. So they have no point of intersection, so therefore they have no solution because they are parallel. And a special thing that you might need to know at some point is that parallel lines have the same slope. So if we were to graph this in a certain way where we get y equaling mx plus b in both of these, we would find that they have the same slope. Okay, let's look at this one. 2x plus 2y equals 6 and x plus y equals 3. Well, this is 2x plus 2y equals 6. This is also x plus y equals 3. If you notice, all I did was multiply this equation by a 2. 2 times x is 2x, 2 times y is 2y, 2 times 3 is 6. This is the exact same line. So how many solutions does this system of equations have? Exactly, infinitely many. Infinitely many solutions. Why is that? Because it's the same line. So the line, every point on this line is an intersecting point of this line because they're the exact same line. Oh, that's my dog. So infinitely many solutions because it's the same line. Probably woke you up with my dog. Okay. So you can see that a system of equations, when you graph them, will show you if you have one point of intersection, no point of intersection, or infinitely many points of intersection. This is page 260, example 1. So we're going to solve a system of equations, and we're going to go way back to when we did substitution a couple of lessons ago, because we got to remember how to do that yet too. So we are going to graph, well, first we're going to solve it with substitution, and then we are actually going to graph it. So let me put a piece of paper here and solve with substitution first. So x minus y equals -2, and negative x plus y equals 4. So we're going to use substitution, and I'm going to change the first equation into slope-intercept form. So let's rewrite these here. And changing that into slope-intercept form, I'm going to subtract an x from both sides. That will eliminate my x's. And I'll be left with negative y equals -2 minus x. We can't combine those. Now I want to divide by -1 to everything on the other side as well. That crosses off my negatives, right? And that'll give me my y is equal to -2 divided by -1, +2, negative x divided by -1, positive x. We're almost in slope-intercept form. We just have to reverse it. Y equals x plus 2. So remember it's slope-intercept form. Let me write it a different color. Y equals mx plus b. B is our y-intercept. Y-intercept. And m is our slope. And we now have it in that format. We have our slope of 1, imaginary 1, and our y-intercept of 2. We could graph that, and we are going to in a moment. So now what we're going to do for substitution is take this y equals this expression and plug that into the other equation up here for y. That was substitution, if you remember back a couple lessons ago. So if I plug that back in, I get negative x, plug it in kind of down here, negative x plus, now I substitute in this for y, so that's x plus 2 equals 4. And then I just solve it for x. So I have a negative x and a positive x. I can combine those. What's that going to give me? Negative x plus a positive x. That's going to give me 0 plus 2 equals 4, right? And then I'm going to move the 4 over to the other side, and I'm going to get 0 equals 2. Is that a true statement? No, you're right. That is a false statement. What do we know when we get a false statement? There are how many solutions? No solutions. No solutions. So our system up here has no solutions. We're going to graph it so we can prove it to ourselves that that is the case. So I have my graph paper here and my system up here that we just figured out had no solutions. So we've already put one of these into slope-intercept form. This one, y equals x plus 2, that's the first one. So we're going to rewrite that. We're going to rewrite that as, this is really y equals x plus 2 in slope-intercept form. What about this one in slope-intercept form? What is that going to be? Let's use our paper and figure it out. So that one would be, originally it was negative x plus y equals 4, negative x plus y equals 4. Let's put that in slope-intercept form. We're going to add x to both sides, leaving us with y equals 4 plus x. We're going to switch that around to y equals x plus 4. So that's the other one in slope-intercept form, y equals x plus 4. So let's write that. Y equals x plus 4. Can't see that. Now you can. So I just rewrote it in slope-intercept form, the pink. So now we can graph it, both of these. So the first one is y equals x plus 2. 2 is our y-intercept where x equals 0. So that's right here, right there. And then we have our slope of 1, the same as 1 over 1. So we're going to go from our point here of intercept, our y-intercept, up 1 and over 1. Okay, that is our line. My ruler here. That is x minus y equals negative 2, or in slope-intercept form, y equals x plus 2. That's that line. Now remember, we decided that this has no solution. So let's do the other one now. So we have y equals x plus 4. So our y-intercept is 4. And our slope is 1, right? 1 in front of x. So 1 up and 1 to the right. And then we graph that. And if I was perfect with my ruler, this is negative x plus y equals 4, or y equals x plus 4, no matter how you write it. Notice that these two lines are parallel, or they should be. My ruler got a little off track here. It really should be more like this. See if I can get it the right way. Something like that. So these two lines are parallel. They will never intersect. And that is why we know that there is no solution to this equation. They will never intersect. No point will make both statements true for both equations. Okay, this is page 261, number 8, your turn. So I wanted to figure out, it wants us to figure out if the system of equations has one solution, no solutions, or infinitely many solutions. So we're going to use our algebraic elimination method to figure this out. So I'm looking at these two and I see that none of the coefficients are the same. I'm going to use elimination rather than substitution, because substitution would be pretty messy with fractions. So what number can I multiply one of these equations by to get rid of one of the coefficient variables? Exactly. I could multiply the second one times positive 4. Right? So if I do that, I'll leave the first one the same. I'll get 12x minus 8y equals negative 4. And the second equation that I will then get is 3 times 4, negative 3 times 4, negative 12x 4 times 2, 8y. 4 times 1, 4. Solving for that, these negative and positive 12s will cross off. I'll be left with 0, right? What about negative 8y and positive 8y? That will also be 0, won't it? So the whole thing is just plain old 0. And on the other side, I have negative 4 plus 4. That turns out to also be 0. So what do we know about that solution to that system? That we have infinitely many solutions. Because remember that if we have a number equaling the same number, that results in an infinitely many solutions. I'll go back to that chart at the end here and show you the 3 possibilities and what it might look like. Let's graph that and see how that will turn out. So infinitely many. So let's see what happens. So we have, I'm going to have to use a separate piece of paper here because I have to get these into slope-intercept form. So before I can graph them, I'm going to get my 12x minus my 8y equals negative 4 into slope-intercept form. So I got to get y on one side and everything else on the other. So first I'm going to subtract 12x from both sides. That eliminates my 12x's. I'm left with negative 8y equals, I can't combine those, so that's really negative 4 plus a negative 12x. Now I'm going to divide by negative 8 to everything on the other side. If I do that, my 2 negative 8's cross off, and I'm left with my y, which is what I want. Slope-intercept form is y equals mx plus b. Negative 4 divided by negative 8 is 1/2, right? 1/2. Negative 12 divided by negative 8. That gives me a positive 3 halves x, if I reduce that. Now I'm going to switch that around so I have it in y equals mx plus b format. Y equals mx is the slope, 3 over 2 is the slope, plus 1/2 is my y-intercept. So now I can graph that one. So I'll make that the blue, well, I'll make it the green one. So that's going to be up here. We know our half is our y-intercept. So I actually numbered these so that every number in between is a half. So this is my half mark. And then I rise 3 and I run to the right 2. So I got to be careful on rising 3 because every one of these squares is a half. So this is 1, this is 2, that's 3, and then I have to go to the right 2, and that's also a half. So 1, 2. You got to be careful when your scale is not exactly 1 to 1. Okay, then I draw my line here, and I'll label that. Good idea to start labeling all this. This is really 12x minus 8y equals negative 4, or the way we rewrote it was y equals 3/2 x plus 1/2. Same thing, just rewritten in slope-intercept form. That's the first line. Now we're going to graph the second line. That's this one, right? So use a different side of the paper here. And we will use blue. So we have negative 3x plus 2y equals 1. And we want to get it in slope-intercept form, so we're going to add 3x to both sides. That should eliminate our x's, or I mean our 3x's. Now we're left with 2y equals 1 plus 3x. We can't combine them, right? They're different. So now we're going to divide by 2 to everything on the other side. That eliminates the 2's. And we're left with y equals 1/2 plus 3/2 x. And then we're going to switch it into y-intercept form. Y is equal to 3/2 x plus 1/2. Notice how that's the same thing. So notice how this is the exact same line as this one, because we have 1/2 is our y-intercept. We rise 3 and run 2. Notice how this line, I'll move this now, is the exact same line. So remember we said that our answer was 0 equals 0, infinitely many solutions. Since this is the exact same line, every point on both lines is a point of intersection, or infinitely many points will be intersecting because it's the same line. Okay, this is guided practice, page 262. So if you need to pause the video to get there, go ahead. Then we're going to go over this page. Let's make a spot here. Okay, use the graph. This is number 1. Use the graph to solve each system of linear equations. So we have 3 systems. We have system A, we have system B, and we have system C. So what we have to do is decide if the graphs of the equations in each system intersect, are parallel, or are the same line. Basically, how many solutions do they have? So system A, let's look at that. That's 4x minus 2y. I'm going to actually circle that. So 4x minus 2y equals -6. That's this one here, which is the line going this way. Maybe I should try to circle that one. That's not going to work too well. So that is this line right here. And the other one is 2x minus y equals 4. That is 2x minus y equals 4. That's this line right here. We can circle that. 2x minus 4y equals 4. Okay, what do we know? System A, the graphs, what? What would you say? Exactly, they are parallel. How do you know that? They'll never touch. They'll never intersect. Oops, I don't want to use yellow. Let's pick red. They are parallel, and they will never intersect, right? So we can go to step 2 for just a minute. Parallel lines have blank points in common. How many points do you have in common between those 2 lines? Exactly. Parallel lines have 0 or no points in common. Okay, so that's one. That would be a system that has no solution. Okay, system B. Grab my spotlight again. System B is 4x minus 2y equals -6. We're at the same line here. And x plus y equals 6. So we're going to get rid of this one this time. Oh, it eliminated my other number. My other words. Put that back in there. Okay, system B. Now I spelled it wrong. That's annoying. Okay, that would have bugged me. Okay, the next one is x plus y equals 6. That's this one right here. X plus y equals 6. And that line is, I think it's the one going the other way. Double check that. Yeah, that's this one here going this way. Okay, what do you notice about the point of intersection, or if there is one? So the graphs, what would we say? They intersect, right? Intersect. Yep. And we can go down here. Intersecting lines have blank points in common. How many points in common do these lines have? Exactly, 1 point in common. So intersecting lines have 1 point in common, 1x and 1y value that will make both lines equal, or a true statement. System C, right here, is 2x minus y equals 4. So let's go and erase what we had circled here. Oh, it erases everything. I don't know why it does that. I want to put that back in there again. Parallel, and the other one was the graphs intersect, right? We have the word intersect in there. Okay. All right. 2x minus y equals 4. 2x minus y equals 4. That's this line here. So let's draw that. 2x minus y equals 4 there. And the other one is 6x minus 3y equals 12. So let's circle both of these right here. That's the same exact line, right? You can see that all we did was multiply by a 3 on the first equation to get the second equation. So the graphs, what would we say about those graphs? What do we say? Are the same line, right? And then we go down here, the same lines have blank points in common. What would you say? Infinitely many points in common. Every single point on that line is the same as every other point on that same line, right? So solve each system. Step 3, system A has 0 points in common, so it has 0 solutions. I think they wanted the word no in the first blank, so we'll just go back and make it a no. No. System B has 1 point in common. And that's in the wrong spot. 1 point in common. That point is the solution. What did we decide the solution was to that? We have to look where they intersect. Go back up here. They intersect at, oh, what did it say in the book? 1, 5. Okay, that was these two lines here. 1, 5. So let me, I'm afraid to erase. It's going to erase everything. There. No, it didn't. Okay, good. Okay, so that was the point right here. 1, 5. Right there. So that solution is 1, 5. 1, comma 5. Should have parentheses around that. And system C has, what are we going to say there? Infinite number, or infinitely many points. Infinitely many points in common. Blank ordered pairs on the line will make both equations true. All ordered pairs. All ordered pairs will make the equation true. Okay? So far, so good? All right, that's using a graph to figure out how many solutions. I just want to bring that chart up. I'm going to have to make it here. So we can remember back from lesson 7.4, insert a table here. Just want 3 columns here. So if we have one solution, or we can have infinitely many solutions, or we can have no solution. I'm going to move myself down over here for that. So if we have one solution and we use the algebra to solve the system of equations, we will get x equaling some number like 6, right? Or we will have, in a case of systems of equations, we will have a point like 5, 7 or 5, 8, some point, right, for x, and for y will make both statements true. If we have infinitely many solutions, we'll get something like 5 equals 5, right, in an equation. Or in a systems of equations, we'll probably end up getting 0 equals 0. Oops. Why does that go where it doesn't want to go? 0 equals 0. And if we have no solutions, we're going to get a false statement like 5 equals 10, correct? Exactly. Okay? So that's how we know algebraically what solution number we have. Just wanted to bring that up. So keeping that up there, let's look at number 2. I'm going to clear my screen. So hopefully got that down. If not, pause the video. 3, 2, 1, gone. Okay, number 2. So down here, x minus 3y equals 4 and negative 5x plus 15y equals negative 20. Solve each system. Tell how many solutions each system has. So we are going to do that here. We'll just do that right here rather than going back under the, I did not do that. Okay, so we have x minus 3y equals 4 and negative 5x plus 15y equals negative 20. I don't want these lines underneath there, so let's get rid of that. And I also want to make these closer together, so let's do that real quick. Okay, that's as close as they're going to get. Now, we want to solve this algebraically. So, what can I multiply one of the equations by to get rid of one of the variables? Well, I see that I have a negative 5 here. Wouldn't it be really easy to multiply by a positive 5? That is what I'm going to do. So I'm going to put brackets around this. And I'm going to multiply by a positive 5 to both sides. And remember, you do that multiplying by every number in the equation. So if I do that, my new equation up here will become 5x plus a negative 15y equals 20. And then if I rewrite this one underneath it, I have 5x plus 15y equals negative 20. You see what's happening? Probably already can see it. When we add these together, we will get, oh, this is a negative 5. We will get 5x and negative 5, and that will cancel itself out or become 0. So let's make it a 0. Let's write the 0 there. 0, right? 0x or 0. What about negative 15 plus positive 15? That's also going to be 0, right? So we'll have 0 plus 0, or just 0, right? Equals, what's positive 20 and negative 20? 0. So we end up with 0 equals 0. So now let's go back up to our chart here. Which one of these would be the way that that looks? Infinitely many solutions. So that is the answer to number 2. We have infinitely many solutions. I'll put SOL for solutions, because now I'm going to run out of space there and go into my second one. So we're going to crunch this way down to here. Like that. Okay. Now the next one we have is 6x plus 2y. I'm just going to clear my drawings now. Do just that. Okay. We have 6x plus 2y equals negative 4, and the other one is 3x plus y equals 4. So we have to figure out which one we can multiply by to get rid of one of the variables. I'm going to pick this one because I see that if I multiply this entire equation by negative 2, that's going to give me a negative 6, which is going to eliminate my x's, right? So I'm going to put a negative 2 there. And then I'm going to leave the first one the way it is. That'll be 6x plus 2y equals negative 4. My second equation then will become negative 2 times 3x, negative 6x, negative 2 times y plus negative 2y equals 4 times negative 2, negative 8. Let me just try to line those up better. And then I'm going to add them so that I can use that elimination method. And if I do that, 6x and a minus 6x, that's going to cross itself off. And a 2y and a minus 2y, that's going to become 0 as well. So both of those are going to give me the 0. So it would be 0 plus 0, or 0, equals Negative 4 plus negative 8. That should be negative 12, right? 0 equals negative 12. That's a false statement. I go way back up here. Which one of these is a false statement? This one, right? 5 equals 10, false. Just like 0 equals negative 12, false. So this one, this system has no solutions. So we're going to put that in. No solution, no solution. And why would that be? Well, if you look at the equation, if you multiply by 2 to every number in this bottom row here, you'll get exactly 6x plus 2y equals negative 4, right? Or negative 2, right? So there's no solution. Those lines are parallel, right? So erase that. Those lines are parallel. They will never, ever intersect, ever, ever, ever. And the last one here, I want to do that. I want to do this. Okay, the next one is 6x minus 2y equals negative 10, and 3x plus 4y equals negative 25. I don't want anything underlined there. See if I have enough space. Yes. So what can we multiply one of the equations by to get rid of one of the variables? Well, I'm going to do this one, and I'm going to multiply it by negative 2. It's almost like the other one, but a little different. So if I multiply that by negative 2, my first equation will stay the same. 6x minus 2y equals negative 10. And my second equation will now become negative 2 times 3x, negative 6x, negative 2 times 4y, negative 8y equals negative 2 times negative 25, positive 50. And then I'm going to use the adding method of elimination to add these two equations together. And I will get 0 here. And over here I'll get, let me just cross these off so you can see that we got 0. 6x and negative 6x will cross off. And then I'll be left with negative 2y and negative 8y. Adding together, that'll give me negative 10y equals, I have negative 10 and positive 50, positive 40. Divide both sides by the coefficient in front of the variable, which is negative 10 and negative 10. Crossing off the 10s because they cancel each other out. I am left with y equals, go ahead, say it out loud. Oops, probably already said it. The computer's going crazy. Y equals 40 divided by negative 10, negative 4, right? Okay, how many solutions are there? Oh, it looks like it erased our other one here. This one was no solutions. So how many solutions is y equal negative 4? Well, we'd have to plug in negative 4 yet, right? So we got to do that. So we're going to plug it into the first equation. 6x minus 2 times negative 4 equals negative 10. Stick with me just a little longer. 6x, negative 2 times negative 4 becomes a positive 8 equals negative 10. Move the 8 to the other side. We get 6x equals, and I'm taking a little shortcut here, negative 10 plus negative 8, negative 18. Oops, move up 1. Why does it decide to do that? Anyways, and then 6x divided by 6 divided by negative 18 will give me x equals negative 3. Took a little shortcut there just because I ran out of room, and so let's just erase all this now. So x equals negative 3 and y equals negative 4, right? So the solution to that equation is -3, -4. That system. That's this right here is our solution. I wanted to highlight that. I'll just circle it. Oops. Yeah, don't want that up. Okay, so if I go back up here, how many solutions did we have? Well, we didn't end up with a number equaling a number. We didn't end up with a false statement. So one solution. So that one, the last system has one solution. Like that. Number 5, when you solve a system of equations algebraically, how can you tell whether the system is 0, 1, or an infinite number of solutions? I would point you back to the chart. Okay? Now, homework-wise, let me clear all my drawings. Homework-wise, that would be right here. So you're going to, well, we did guided practice page 262 together, but please turn that in. That way I know you watched the video and that you did the work. Independent practice, page 263 and 264. Do not do the hot problems unless you want the extra credit. And I also do want you to do IXL systems of equations, and I can actually show you that. I want you to do number 4 and number 5, finding the number of solutions of to a system of equations by graphing, and also finding the number of solutions to a system of equations just without graphing. So let's look at that. I think I have that up. Let me pull that up for a minute. Okay, so here, systems of linear equations, number 4, oops, number 4 right here, and number 5 right next to it. So I want you to do those two. So I have a form on the Google Classroom saying, yes, I did this, and then I can go in and look and see if you actually did it. So you'll fill out the form and say, yes, I did it, and then I know to go look and see that you did do it. So I am going to stop my share. And if you have any other questions, I realize that this unit is definitely a difficult unit, but we're at the end of it now. So we'll be ready for review next. So have a good day. Bye.